This video is about simplifying radicals. This is a radical. This mathematical symbol here, we call the thing underneath the radicand, and there are more than just square roots. A lot of times we call this symbol the square root symbol. That's okay. Most of the time when you see it, a radical is just showing you the square root. Now, if there's ever a number out front, like if I put a 2 out here or something, well, that's still called a coefficient. Just like if I had 2x, the 2 would be the coefficient. Well, that is still the coefficient. Just so you know what the heck I'm talking about when I talk about the different pieces of these. So the square root is literally the opposite of raising something to a power. So if it's the square root, not the cubed root or the fourth root or anything, then it's the opposite of squaring something. So 4 squared is 16. The square root of 16 is 4. It's an inverse operation, really. These are perfect squares, meaning when I take the square root, it's a nice, simple whole number. And I strongly suggest that you just copy them in your notes, maybe memorize them. You should be familiar with these. A lot of people are at least familiar through 12, and honestly, that's probably good enough. It just saves you time and effort if you're familiar with these. If you're in my class, you get to use your notes for tests and things, so copying them in your notes would be really, really handy. It would probably save you time on quizzes and tests. Of course, it's a video, so you can pause it if you would like to do that. So starting off simple with just the perfect squares. The square root of 4 is 2 because 2 times itself is 4. The square root of 16 we just looked at. That's 4 because 4 times itself is 16. The square root of 25 is 5. The square root of 100 is 10. The square root of 144 is 12. You get the idea. If I take the answer of any one of these and I square it, I get the radicand. If they're perfect squares and you realize that they're perfect squares, meaning if you just know the answer, well, just write it down and move on. Now, we will be putting answers in what's called simplified radical form. So even if they're not perfect squares, even if they're not on that list that I gave you, we're gonna simplify things. We're gonna shrink the thing under the radical, the radicand, down and make things look a little nicer, but without decimals. A lot of times when you take the square root of something that's not a perfect square, usually you get a decimal that goes on forever and ever and ever, and it just keeps going, and then you have to round. So then your answer's not completely correct anymore when you round. So we'll be doing simplified radical form. It's going to involve a lot of factor trees. So when you think square root or roots in general, think of trees, factor trees. This is a factor tree for 54 because 6 times 9 is 54. And then 3 times 2 is 6, 3 times 3 is 9. And we have these factors at the end. These are our prime factors, which means the only other factors is the number times 1. And that's not useful to us, which is why we stop here. This means I could write 54 as 3 times 2 times 3 times 3. 3 times 2 times 3 times 3. If I multiplied these numbers out, I would get back to 54. Now, for our steps, because I have some steps here, and just kind of a side note, if you recognize something, if you recognize a perfect square at some point in your factoring, and you realize what you can do with it, you can jump ahead. But if you're not recognizing, if you're not noticing things like that, well, these are the steps that work every time. Factor all the way to prime numbers, to prime factors. That's like that factor tree I just showed you. Look for matching pairs of factors. Each pair of factors from the radicand becomes one factor outside of the radical. I will show you exactly what I mean by that. Any single factors have to stay under the radical. That means if they don't have a pair. Let's see what this looks like. Let's see. Okay, we're going to start with this 8. So it's not a perfect square. I'm going to go ahead and make a factor tree. 8 is 4 times 2. 4 is 2 times 2. And then I'm looking for matching pairs. I have a matching pair of 2's right here, and then I have 1, 2 that's all alone. My matching pair of 2's on the inside becomes a single 2 on the outside of the radical. It becomes a coefficient. My lonely 2 that has no pair goes back under the radical. It's stuck there. This is simplified radical form. Square root of 8, or radical 8, is the same thing as 2 radical 2. Let's try with this 32. Once again, I'm going to do a factor tree. 32, let's see, that's 4 times 8. 4 is 2 times 2. 8 is 2 times 4. 4 is 2 times 2. So I've got all the way down to prime factors, and I'm looking for pairs. So I have a pair of matching 2's right here, and I have another pair of matching 2's right here, but don't forget this lonely 2 that has no friends. So I've got a 2 from here, and then I have a 2 from here. They're both on the outside. Each pair becomes one single 2. And then my lonely 2 that has no friends is stuck under the radical. Notice that it's all multiplication. This between the coefficient and the radical is multiplication. This between the 2 separate coefficients is multiplication. So really this simplifies to 4 radical 2 once I multiply those 2's together. All right, problem number 3, let's try it again. One of my teacher friends refers to this as radical prison, and I love this example. So, the radical is a prison, and the radicand is trapped in prison. Let's see who's in the prison here. We've got some factors. Here's some prime factors. So we've got some 2's that are in radical prison, and another 2, and a 5. And these are prime factors. So the 2, the other 2, and the other 2, and the 5, all these factors are trapped in radical prison. I don't know what they did, but it must have been bad. Well, if 2 of them can team up, they can dig a tunnel and try to stage an escape from radical prison. This 2 and this 5, well, they're not willing to work together. They have no real friends. They're just going to lay down on their cots and they're going to accept their fate and stay in prison. But these 2's, they're digging a tunnel. They're going to escape. Except, as always happens in radical prison, one of them dies in the process. I don't know. Maybe there was a prison tunnel collapse. So only one of them makes it to the outside. And then the 2 and the 5 are just still inside. They're like, forget it. Your escape plan is dumb. I'm staying here. Kind of goofy, but also memorable. All right, let's try a few more here. Okay, I've got a 20. Well, that's a 4 times 5, and a 4 is a 2 times 2. Pair of 2's, so I will have 1, 2 on the outside, and then the 5 goes onto the inside. Now, I mentioned if you see something like a perfect square early on, you can jump ahead. It's definitely possible that we could have seen a 4 and went, oh hey, the square root of 4 is 2. I know that the square root of 4 is 2. This 4 just becomes a 2 on the outside. And we didn't have to actually write the 2's down because we know the square root of 4 is 2. That is a possibility that you should only do if you feel like you really understand why it works. All right, so 25, I'm looking at it, I'm going, no, that's 25 times 3. And if you're thinking, like I just pointed out, you might notice, hey, square root of 25 is 5. So it's 5 on the outside, 3 on the inside. If you know what I'm talking about, go ahead and do that. If you don't know what I'm talking about, well then just keep going and make the 25 into a pair of 5s. A pair of matching 5s, which means the 5s are going to stage a prison break. The 3 is not. He is not friends with the 5s, and he's just gonna go lay down on his cot and, I don't know, give up on life and stay in prison. So the 5s, one of them dies. But one of them makes it to the outside, and the 3 is just hanging out in his cell. All right, I have a couple more. Notice the main difference with this one. There's already a number out there, which is totally fine. That 4 is gonna hang out there. I'm gonna do the same thing as usual with my 99. Oh, 99, well, I know that that's a 9 and an 11. And then I know that 9 is 3 and 3. If you're in my class, I have factor charts for you, by the way, if that is helpful. So I have a pair of 3s. They're going to stage a prison break. The 11 is going to just stay there. So I'll have 1 3 that makes it to the outside. The 4 is going to still be there, okay? I don't know, the 4 is the outside man waiting for the 3 to escape. The 11 is still in here. And notice again, this is multiplication. All of these things are being multiplied together. So this is 12 radical 11. I only have 2 more problems and then this video will be done. I've got a 27, this is 3 times 9, and 9 is 3 times 3. So right away, I see I've got a pair of 3s and I have 1 lonely 3. Now, note the negative sign on the outside. This is the same thing as a -1. And this negative sign, or -1, however you want to write it, it's just going to stick around. So I have the 3 from here, the one that survived the prison break, times the -1 that was already there. And then I have this 3 that's still on the inside. And the 3 times -1 just turns into -3 on the outside, meaning -3 radical 3 is my final answer. All right, one more. This is my last problem. Similar to the last couple problems, the 12 is just going to hang out. And I'm looking at 138, and I don't really know what goes into 138. I know that it's an even number, so I'm going to start with that. And it looks like it's 69 if I divide 138 by 2. And seriously, if it's an even number, just divide it by 2 and see what you get. If it's not an even number, you can try 3 or 7. If it's divisible by 5, that's very recognizable because it ends in a 0 or a 5. Just try dividing it by some things. Okay, and 69, well, I know 3 goes into that, and it goes into that, what, 23 times? I'm getting, like, nowhere. So I've factored it down. I don't have a pair, and 23, I believe, is prime. Okay. Not everything's going to factor. Some things are already as simplified as they're going to get. But always give it a try first, because if there was something that you could have pulled out and you miss it, yeah, then you're wrong. So make sure you give it a try.